Hi everyone. Good morning, good afternoon, good evening, depending on where you're joining us in the world today. I'd like to thank you for joining us. Welcome to today's CNCF webinar. CNCF has 99 plus K8 distros, and this is how and why we built one more, OKD4 on FCOS. I'm Christy Tan. I'll be moderating today's webinar. We would like to welcome our presenters today, Christian Gombeck, Vadim Rostovsky, Charo Ruver, and Dusty Maeve of Red Hat. A few housekeeping items before we get started. During the webinar, you are not able to talk as an attendee. There is a Q&A box at the bottom of your screen. Please feel free to drop in your questions and we'll get to as many as we can at the end. This is an official webinar of the CNCF and as such is subject to the CNCF Code of Conduct. Please do not add anything to the chat or questions that would be in violation of that Code of Conduct. Basically, please be respectful of all of your fellow participants and presenters. Please also note that the recording and slides will be posted later today to the CNCF webinars page at cncf.io/webinars. With that, I'll hand it over to Christian, Vadim, Charo, and Dusty to kick off today's presentation. Take it away, everyone.
All right. Good morning, everyone. We're going to be talking to you this morning about a Kubernetes distribution that we've been working on for a while, just went GA earlier this summer. The agenda we're going to cover today is first just telling you what OKD is. From there, we're going to jump into an overview of operators and the operator framework, talk specifically to you about the MachineConfig operator, and then go further down into the stack to Fedora Core OS, and finally close out with a demo and your questions. So without further ado, what is OKD? So OKD4, right? Many of you are probably familiar with Origin, which was an earlier evolution. You've probably seen MiniShift. And now we're introducing this Kubernetes distribution we're calling OKD version 4. So OpenShift went through a significant evolution from version 3 to version 4. OpenShift Container Platform being the officially supported Red Hat product, right? So the introduction of operators and Core OS were probably the most significant changes. This move changed OpenShift really from a platform that is built on Kubernetes to a self-contained ecosystem with Kubernetes at its core. Important distinction there, Red Hat OpenShift Container Platform 4 is open source like all Red Hat products, but the images require a subscription to access. So we wanted to deliver on the open source promise that Red Hat has at its core and continue to provide a freely available version of OpenShift for everyone in the community. OKD4, previously called Origin, is the fulfillment of that promise. And unlike some of the other community projects that Red Hat participates in and sponsors, OKD is not exactly upstream of OpenShift Container Platform. It's more like a parallel stream is how we think of it internally. It shares the same code base as OCP, but where OCP is leveraging Red Hat Core OS as its runtime operating system, the underlying operating system of OKD is Fedora Core OS, which we'll discuss quite a bit more in just a bit. So while the main code base of OKD is OCP, there are some upstream elements, Fedora Core OS being a good example. OKD also delivers releases in a faster cadence than OCP, so you do get to try out new features, fixes, and sometimes bugs sooner than everyone else. In fact, if you're extra brave, you can even build and update your clusters from our nightly stream and take a look at what is currently under development. Like OpenShift Container Platform version 4, OKD4 is more than just Kubernetes plus some stuff. It's really more of an opinionated yet highly flexible Kubernetes-based ecosystem. It's built around the relatively new concept of operators, which we'll get into more in just a bit. But for now, let's just say that operators enable the automation that really sets OKD apart. Through the operator framework, OKD manages your entire platform. Automated installation, automated patching, automated updates, and maintenance of the entire environment, and very significantly, including the operating system itself. The operating system that's bundled with OKD4 is Fedora Core OS, which we'll also go into in more detail here in just a bit. Fedora Core OS is automatically installed and configured on your platform of choice as part of the OKD installation. Its full life cycle is then managed by OKD through a set of specific operators. It's deployable on many different infrastructure platforms, from bare metal to cloud. We've got a very small sampling here of what's possible. It's really suited for a wide array of deployments. You can do small edge clusters. You can build out massive compute workloads with OKD. You can deploy a single node if you're willing to forego high availability. You can deploy a highly available 3-node cluster where your worker nodes and your control plane nodes are sharing roles. Or you can deploy a full enterprise-grade cluster with dedicated control plane, infrastructure, and worker nodes. If you want to know more, take a look at the installer project in GitHub under github.com/OpenShift/installer. There you'll see all of the available deployment platforms and configurations. At the end of this, there'll be a slide with some more links for you to get more information. And that really covers our high-level overview of OKD. Now we want to dive into some of the details. I'm going to turn it over now to discuss the operator ecosystem that provides the base of automation for our environment. Take it away, Christian.
That would be me.
Oh, is it Vadim? Vadim, take it away, Vadim.
Sure. The core difference between OKD3 and OKD4 is that the new distribution is built around a whole new pattern of how we deploy, of how we package and manage the whole distribution. This pattern is called operator pattern. And the core difference between other ideas of how you can deploy applications to Kubernetes is that operators are self-managing. They are controlling resources they have created. And they are constantly watching and ensuring that they have reached the desired state. It also includes core Kubernetes capability of having custom resource. So this is the way operators are communicating with the users. They can also reuse the very same custom resource to communicate with themselves and store the information in etcd for the later consumption. Next slide, please. Here are the list of operators which we're using in our distribution. The very top level operator is called cluster version operator. It ensures that all other operators are deployed. They have reported they are successful. No errors are available. And all the necessary parts of the platform have been established so that we can call it a successful deployment. Other list of distributions which are handling the core Kubernetes parts like Kube API server, Kube controller manager, Kube scheduler, and etcd are also controlled by operators, and they ensure that they have reached the necessary state, they have the necessary configuration, and they can pass along the configuration between them. Operator pattern in this case is incredibly useful because it ensures that a large list of all possible Kubernetes API options is condensed into a small set of specs in custom resource, and operator is also taking care of updating those items between one version to the other, and it can stop if some kind of issue occurs. It can update just one instance instead of trashing the whole API server, for instance. Also, network operator is taking care that CNI plugins would be placed on the host and necessary configuration for the SDN is deployed. Some more high-level operators ensuring that other capabilities of the cluster are deployed, like image registry, monitoring, ingress, which ensures that the router is set up, and other parts like storage are also communicating with themselves and with the core operators, and ensure that the resulting platform has necessary state. That also simplifies testing in our case, because we can change just one operator part instead of testing the whole platform of how the different items are intertwined between themselves. Next slide, please. OKD4 is also supporting other optional operators, and we have created a site called operatorhub.io, where users can upload their own operators, share themselves between the whole community, and update them using operator lifecycle management. The examples of these, for instance, Grafana, Argo CD, KubeFed, and many, many others. Operator lifecycle management has recently become a CNCF project, if I remember correctly, and it takes care of installing the operator, setting necessary permissions. For instance, it can be a cluster-wide, or it can be watching just one namespace. And it allows administrators to delegate permissions to install instances of the operator in different namespaces, so it takes care of that. Operator Hub is also integrated in OKD's console, so we can see how you can self-service in a self-service way, install additional operators. We'll display that during the demo. And with that, I'll pass it to Christian, who would explain one of the core operators called MachineConfig operator.
Hi, everybody. I'm Christian Glombik, talking to you from Hamburg, Germany. So good morning, good afternoon, good evening to all of you. So yeah, the MachineConfig operator is a core operator in OpenShift. In contrast to the operator hub operators, which can be installed on top of the core cluster, all of our components in OpenShift are actually driven by operators to allow for our really, a cluster on autopilot, essentially. So as Vadim just explained, the operator will take care of reconciling the desired state and getting back to where we want on all the nodes and all the parts of the system. The MachineConfig operator is a little bit special because it's our secret sauce for updating the cluster and its base operating system on the nodes. So what the MachineConfig operator does is it manages the machine configuration and allows for customization of configuration. We have a format which we'll go deeper into in a bit called ignition. And ignition is used to describe our desired state. So what the MachineConfig operator does here, it takes the machine configuration objects, which is a CRD, and renders them into a canonical desired state for our cluster. We have different pools there, so you can have different configuration for masters and workers. And then it reconciles all machines in the cluster with that desired state. And it's also in charge of updating the operating system underneath. We use an RPM OS tree image-based approach to delivering our operating system. I think we'll get into that a little bit as well. We deliver our The OS tree commit. OS tree is used in many different other projects as well, like Flatpak, you may know. We deliver the OS tree, which represents the on-disk contents of the operating system, in a container, and then the MachineConfig operator, when there's a new version available, notices that and unpacks that container and writes it onto disk and reboots the entire cluster in a safe manner. So it does everything. It shuts down etcd safely and drains the nodes, and then reboots if that's safe. So let's have a look at the MachineConfig CRD. This is controlled by the MachineConfig controller, which is part of the MachineConfig operator. So as you can see, we have a few high-level fields in that struct. First, it's the OS image URL, which points to our operating system payload. So in our case, in OKD, this is Fedora Core OS. It's an OS tree embedded in a container. And then we have the config field, which is a raw extension here. This is where we put the ignition configuration in. The MachineConfig operator actually allows for parsing different versions of that, but internally it'll translate everything to ignition version 3.1. Yeah, we have a few more fields here, so you can actually define kernel arguments that'll be applied on the next reboot if it's rendered into the rendered MachineConfig, the canonical state. We also allow for extensions, which is additional RPM packages to be installed on top of the base image in a transactional manner. Then we have the FIPS Boolean variable. This hasn't been tested on Fedora Core OS. And we have the kernel type, which is also nowadays just used on Red Hat Core OS. But technically, it should be possible to deliver different kernel types to Fedora Core OS if you create your own payload as well. Next slide, please. So part of the MachineConfig operator is the MachineConfig daemon, which runs on the nodes, on the actual hosts. And that takes the rendered MachineConfig and applies that to all nodes to enforce that state and reconcile against the desired state. Now, the MachineConfig daemon supports a subset of ignition configuration for customization. That means while ignition config is usually consumed by the ignition binary, once the cluster is up, the ignition binary ignition doesn't run again. It only runs at the very first boot. So the management of that configuration is then taken over by the MachineConfig operator and enforced by the MachineConfig daemon. So we allow for writing files and writing systemd units for services at a later stage in the cluster lifecycle. It updates the underlying operating system by pulling the OS tree commit from a container, which is the machine OS content container in OKD. And then it writes that to disk, switches up the bootloader ordering, and boots into that new commit. And with that, I'll hand it over to Dusty.
Hey everybody, my name's Dusty Mabe and I'm coming to you from Raleigh, North Carolina this morning. And good afternoon and evening to people who are in all kinds of other time zones. Okay, so I'm going to talk about Fedora Core OS and I'm going to give you a long-winded sentence up front. I'm going to say Fedora Core OS is an automatically updating, minimal, monolithic, container-focused operating system designed for clusters, but also operable standalone, optimized for Kubernetes, but also great without it. Next slide. However, I like shorter sentences and more to the point. So basically in 2 sentences, Fedora Core OS is an auto-updating container OS, and you can run it with Kubernetes or without it. Specifically for this audience, the Kubernetes part. So let's talk a little bit more about how Fedora Core OS came about. Fedora Core OS came from the merging of two communities. One of them was the CoreOS company's Container Linux community, and also Project Atomic's Atomic Host. So how did we merge these two things together? Fedora Core OS itself kind of pulled from the Container Linux philosophy, the provisioning stack, and the cloud native expertise. Specifically on the philosophy, you'll see a lot of what Container Linux tried to push forward in the industry in Fedora Core OS itself in the features that I'm about to talk about. And from Atomic Host, we took the Fedora Foundation, the update stack from Atomic Host, and also the SE Linux enhanced security from Atomic Host. Next slide. So let's talk a little bit about the features. Next slide. So the first feature I'll talk about is automatic updates. In the context of OKD, the cluster manages the updates. So this one is a little bit more focused on standalone use cases or cases where the cluster doesn't handle the updates itself. But in general, Fedora Core OS delivers automatic updates by default. And in order to achieve automatic updates, the updates need to be reliable so that users don't turn them off. If an update breaks every other week or so, people aren't going to sign up for that. So in order to deliver reliable updates, we have extensive tests in our automated CI pipelines to try to make sure that use cases that we know about don't regress. We also have several update streams, which I'll talk about a little bit more here in a minute, to preview what's coming. So users run the various streams to help find issues. And then also, if we do find an issue with an update, we stagger upgrades over several days. So for example, if the first 10% of people who do an upgrade hit a problem, then we'll actually halt the rollout and stop it. So the next 90% of people don't hit the problem, and we'll investigate and try to figure out what's wrong. But inevitably, things do go wrong sometimes. So when things go wrong, we have RPM OS tree, which allows you to roll back to the previous deployment and basically get back to your old functionality while we investigate what happened with the update that wasn't good. In the future, we would like to have the rollback happen automatically based on a user-specified health check. Next slide. And I mentioned in that previous slide multiple update streams. Want to go into that just a little bit more. Currently, we have three that are essentially production streams. One is called Next. This is experimental features and Fedora major rebases. So basically, if a new thing comes that we want to experiment with, call it C groups V2 or something like that, it'll usually land in our next stream first. Testing is essentially a point-in-time snapshot of Fedora stable content, and it's a preview of what's coming to stable. So what we'll typically do is, today we'll snapshot and put out a testing release, and then in 2 weeks, hopefully we haven't found any issues with that release, and then we'll promote that content to stable. So the goals of having these update streams is to publish new releases into update streams every 2 weeks. So release often, and then also find issues before they hit stable so we don't break people. Next slide. The next feature I want to talk about is OS versioning and security. So Fedora Core OS itself uses RPM OS tree technology. I think Christian and Vadim mentioned that earlier. I like to describe RPM OS tree as like Git for your operating system. So you essentially get a single version identifier or commit hash, and that tells you everything you need to know. So the version is kind of like a tag in Git, and the commit hash is like a commit hash in Git. And so when people have issues and they want to report a problem, they tell us what version they're on, and we can immediately try to reproduce that problem, on our own systems, as long as we pull that same content. It also allows us to traverse history and find exactly when a new problem was introduced in the history of the OS. RPM OS tree itself also uses read-only file system mounts. This helps prevent accidental OS corruption. So if somebody does an RMRF on a wrong directory, and it also prevents non-sophisticated attacks from modifying the system. But for more sophisticated attacks, hopefully SE Linux itself being enforcing by default will kind of prevent some more sophisticated attacks. So for example, if an application gets compromised, hopefully it doesn't spread to where that application can then mess with other containers running on the system or the host itself. Next slide. Next feature is cloud native and container focused. So container focused, yay, software runs in containers. By default, we have the Podman or Moby engine container runtimes, which is Docker. And then for OKD, we run everything in Cryo. And then, you know, Fedora Core OS at its core is ready for cluster deployments. So you can spin up 100 nodes and have them join a cluster, or you can spin them down and spin them up again whenever load decreases or need decreases or increases. Really, the way this is achieved is through our automated provisioning with Ignition, which I'll talk about here in just a minute. And the other thing here is we're striving to try to be, you know, available in whatever cloud that you might be trying to use, and also bare metal. So we're trying to be ubiquitous there. Next slide. This one, automated provisioning. So Fedora Core OS uses Ignition to automate provisioning. You've heard the word Ignition quite a bit throughout this presentation, and it really is a core component of, you know, of the solution here with OKD. So with Ignition, any logic for the machine lifetime is encoded in the config, whether it be, you know, everything that the machine's ever going to need, or whether it be something like, hey, here's the information you need in order to join a cluster that's going to help manage you, which is the case for OKD. So with Ignition, since you're providing all of that information up front, it's very easy to automatically reprovision nodes. So this means if you lose a node, it theoretically is not a big deal because you can just spin up another one and you've got all of your configuration information there. Hopefully you haven't hot fixed anything on the node. So Ignition also allows us to do things in, you know, bring the more cloud native feel to other places like bare metal. So for example, with Ignition, we use the same starting point, whether you are on bare metal or whether you're in the cloud. As opposed to, in a more traditional way, using Kickstart for bare metal and Cloud Init for cloud, you had two different ways of provisioning your systems. Now you have one, and you can use Ignition pretty much everywhere. Next slide. So the details of Ignition. Ignition is JSON, machine friendly, usually provided via user data. It runs exactly once during the initRMFS stage on first boot. This means that you know, this is another point later in the slide, but if provisioning fails during that initRMFS stage, the boot fails, or otherwise known as the boot just doesn't continue. So if Ignition fails during the initRMFS stage on boot, it won't continue to boot into your system. This is nice because you won't end up with a system that's half provisioned and half running. So maybe, you know, part of your app is up and working fine, but the other half is not working, and you won't figure that out for a day or two or something like that. With Ignition, it's really nice that you won't have that problem. It might be a little harder to debug up front because the initRMFS is not fun to debug in, but you at least won't have that problem. Ignition itself can do quite a bit of things, but we have a set of primitives. We can create files, write system to units, create users groups, partition disks, create RAID arrays, format file systems. Yep, you can format file systems. It's kind of cool. An example MachineConfig is over on the right-hand side. This is just very basic, creating a user and setting an SSH key for it. However, Ignition configs aren't very friendly. You don't want to hand write one. So what we have is a tool called the Fedora Core OS config transpiler, and that can be used to actually handwrite YAML that will generate Ignition configs from that. And it's not just a YAML to JSON converter. There actually are quite a few little helpers in there that just make things a lot easier. Next slide. So how are all of these features of Fedora Core OS used in OKD? First off, automated provisioning. So I just talked about Ignition. OpenShift install, the tool that installs OKD clusters, generates Ignition configs. And then when each node is started, the Ignition itself applies the configuration, and subsequent processes on boot join that node to the cluster, and then the cluster manages everything from there. And just an example of how complex or how much work is actually being done via Ignition, a single bootstrap node that's used to bring up an OKD cluster from scratch has an Ignition config of around 300 kilobytes. So that's a lot of data that's being conveyed in the Ignition configuration in order to bootstrap a cluster from scratch. So it's a pretty powerful tool. The next feature, OS versioning and security. So OKD builds on top of Fedora Core OS, and you know exactly what was delivered and running. So this makes bug reporting easier. If you remember me saying earlier, RPM history is like Git for your operating system. So you know exactly what was delivered and you know, if a bug existed in that particular version or whatnot. Cloud native and container focused. So new nodes are easily added to the cluster via the machine API plus Ignition. I think Vadim might be going to give a demo of that here in just a minute, but you know, it's as simple as if you're on a particular platform that machine API supports, like GCP or whatnot, it's as simple as editing a machine set and adding a node, and you get a whole new node added to your cluster. Everything is done behind the scenes for you. The node started with an Ignition config, it joins the cluster, and then it just starts chewing off work. And then the last thing is software runs in containers. Woohoo! Okay, and automatic updates. So new releases of OKD can be applied automatically or with the click of a button. Next. So a recap. What is Fedora Core OS? It's an automatically updating Linux OS. It's aimed at containerized workloads based on RPM history and Ignition, composed of Fedora RPM packages, and it's great for running Kubernetes clusters on top.
All right, Vadim, I'm going to stop sharing so that you can take over the screen. You should have control now.
Okay, so let's start with the demo. Dusty has mentioned OpenShift install in his previous slides. This is how its output looks. There are two modes in the installer. Basically, first of them is called installer provisioned infrastructure, meaning you tell installer, give me a cluster with 2 workers and 3 master nodes. Here are my AWS credentials, and it does the rest. It creates machines, it creates Route 53 records, and so on and so forth. And in approximately 40 minutes, it gives us a URL, a kubeadmin user, and its secret password. So once we log in, we would see an overview of the cluster. It shows us the main points of what an admin requires to check the health of its cluster. All the parts seem to be working, including more details about the control planes and the operator status, its utilization, and the main parts of inventory, basically how many nodes, pods, storage classes, and so on we have here. So speaking of Fedora Core OS, if we go into the details of the node, we'll see which version of the Core OS it's running. It runs a rather recent kernel, and it uses Cryo as a container runtime. In the cluster settings, we'll see more details about which operators are used to form a cluster. There is about 30 of them, and each of them are applying their status and what's their basic generic health. Speaking of the operator pattern, the high-level operator, it's called cluster version operator, is constantly trying to reach the desired version and ensures that all the resources it has created are reporting healthy and just exist. For instance, if we remove one of the deployments it has created, a whole operator, we would see that after a couple of minutes, it would find out that it has lost something and would recreate. We'll get back to that later. Meanwhile, speaking of Fedora Core OS and how operators are interacting with them, there is also an operator called Machine API, which implements cluster API for each particular platform we support API on. It ensures that you can control the resources like the machines in AWS or GCP. You can control them from the console of the cluster itself, and you can create additional machines which would later on join as workers. For instance, here we have 3 machine sets, each different availability zone. And if we would request another machine here, we would see that a machine object has been created. Machine API operator would notice that, creates an actual machine in AWS. And in about 5 minutes, it would join the cluster as a node. What Machine API operator does is it's contacting AWS, GCP, or some other platforms provisioner, ensures that a new machine is created, and it gives it an entry point where the machine should get its configuration. For instance, if we provision a worker, we would ask it to fetch the worker configuration. This config is stored at so-called MachineConfig pools. We have 2 different configuration sets, one for masters, one for workers. It's composed out of the set of configuration sources. This one, for instance, contains my public SSH key so that I could later on, so that later on I could SSH into that machine and verify that all of these parts that MachineConfig contains are literally ignition files, the very same you use to configure Fedora Core OS. So when the node is actually created, it gets it MachineConfig from MachineConfig operator, and later on it joins the cluster. We'll return to that in about 5 minutes, and it would, the node actual reference to the node object would appear here. Oh, I was kicked out. Our console is also integrated with the monitoring operator we have here. So for instance, we can run queries against the Prometheus and see, for instance, the load average for some nodes. That also includes alerts and alert manager. So we can see that some alerts are firing, but none of them are critical. Let's skip those and jump to the fun part. So the way the whole distribution is built around the operators, it's upgrading a distribution from one version to the other is much simpler because it's just a matter of upgrading a top-level operator and letting it reconcile the rest. So that means we can include over-the-air upgrades. And when you click a button on the console, you would see different versions. Let's pick this one. And when we click update, we'll see that an update is being downloaded. And once it's done, we'll see that some operators are switching status to updating. And once they resolve, your cluster would switch the version, basically. We're building all our updates on our CI system. We're ensuring that these are passing tests. So no nightly which doesn't pass conformance tests. All of those nightlies would be rejected, and only those which are passing would be accepted. And we ensure that images can be upgraded from one version to the other. And if it's a success, the user would see this on the console. The console also has a cute developer-focused view. So you can get away from all those complicated Kubernetes objects and go back to simple developments, to developer configs, for instance, see a list of pods in a more simplified fashion, and see how they interact with each other. On OKD.io site, you would see some more screenshots from our users and the community contributed experience. And another thing which I wanted to demo was Operator Hub. So we can see that operatorhub.io and optional operators are integrated in the console. We could have a look at some of those, install them, get more explanation on what it is, how to use that. And we can also look into installed operators. For instance, OpenShift pipelines based on Tecton project is integrating itself into the console, and it adds a new section with the pipelines. And for instance, in this namespace, I have a Grafana operator installed where I would see its version 3.5. I could change channels to switch between different speed of upgrades. And I could see the custom resources this operator controls and has created. Let's check on in back. So speaking of the cluster version, it has recreated the operator I have removed. Our machine has been provisioned to the node, and this cluster is being upgraded. For now, as you can see, thanks to the user, that's because we're using 3 masters. We can upgrade one by one without affecting the API availability. So I can use the console while the cluster itself is upgrading, and no user workloads are disrupted during the upgrade. On GitHub on OpenShift/.okd, we're collecting issues which are specific to OKD, and have a nice frequently asked questions page where a lot of user contributed questions have been answered, and we would like to extend it later on. That's my demo. Thank you.
All right, I'll flip it back to our screen share. Okay. Dusty, you want to talk to us about the Fedora Core OS Working Group?
Yep. So the Fedora Core OS Working Group is kind of a collection of community members that are interested in the development and the future direction of Fedora Core OS. We have an IRC channel, Fedora Core OS on Freenode. We have an issue tracker, which is kind of where we have a lot of discussions about the future direction. We have a discussion forum, which is kind of more user focused as far as like, hey, I'm trying to do something and it's not working. So people will try to go there first. We also have a mailing list, kind of low volume. And then I do encourage people, if they are interested in the direction or just kind of seeing where we're going, we have a weekly meeting, and that currently happens on Wednesdays, actually in about 2 hours from now. So convert that to your local time zone, or you can go to the link there, apps.fedoraproject.org/calendar/coreos, and that will let you know when the meetings are and convert it to your time zone for you. So yeah, if you're interested in Fedora Core OS, come join us.
And likewise, we have an OKD working group. Vadim and Christian are co-chairs of that group. You can see the links here. We've got some Slack channels where we're all pretty active. We do have bi-weekly meetings. The link to the calendar is right there. And we maintain most of our information in the 2 repositories listed below. The OpenShift OKD that Vadim was showing you is the more active, because that's where we're tracking our issues and where new releases of client bundles get posted. The slide is just some link eye candy for you to get more information. And I believe that concludes the talking portion of our webinar.
Maybe just to add to that, if you want to participate in OKD, please join the working group. We're also working on our roadmap together with the community. So we have reached this milestone of GA release now. And the next thing, or the thing we're focusing on right now, is getting all the bespoke operators tailored for OpenShift that Red Hat usually delivers as a product. Also, to get them released as a community operator, working specifically well and with OKD. There's just a little bit of process. We have a lot of operators that aren't yet released for OKD, but we have a wish list for the community, and we're working on getting those operators all to work on OKD as well. So if you want to participate, if you have any wishes, any issues, or anything really, if you want to just participate or listen in, please do join the working group.
All right, we've got some questions that are starting to trickle in now. First question, just went away. Oh, because Vadim just answered it. Yeah, the question was, is the demo on AWS? The answer to that was yes, but could easily be GCP or OpenStack. And if you go to docs.okd.io, you'll see a full list of the platforms we support. Next question. It's trying to create a big data dev environment using bare metal Hetzner machines because of the excellent cost for RAM, currently using Ubuntu and Ansible to set up, including user access, home folders, disk partitions, IntelliJ, and other development tools like VirtualBox, etc. What I think about using OKD for this, given the strict control that it has over the setup. Does it make sense to use OKD for this type of an environment? And I'd say, Vadim, you and Dusty and Christian could probably take this based on the amount of customizations that can be done via Ignition and the MachineConfig operator.
Yes. Hetzner is not an ideal platform for us because it doesn't implement cluster API. So that means you won't be able to scale machines just like I did on the demo. You would have to have a different implementation for that. But once that appears, we could include it in OKD, and that would work just like it does on AWS. There is
yes. So in that case, basically somebody would follow the user provision infrastructure documentation for that, right? So OKD can definitely be used there. It's just not as easy, right?
Correct. Apart from that, there is nothing wrong with it. I'm pretty sure I've seen a Hetzner repo related to OKD, as in examples of how to get deployed. So that shouldn't be too tough. You would just have to use a bare metal installation and take care of all the infrastructure bits yourself, unfortunately.
Yeah, and the FCCT tool that Dusty mentioned earlier is great for customizing your Ignition configurations to add features, customizations to the nodes when they get built. Next question is, how different is OKD4 to OCP4, the code base? Are there any feature differences?
I think I'll take that one. So we're exactly the same code base right now for all the operators. The only difference is the installer referencing a different set of base images for the different clouds. So yeah, we use Fedora Core OS, as you just learned, in contrast to Red Hat Enterprise Linux Core OS. So yeah, in terms of features in the core, OKD install, everything is the same. I was just touching that point with regards to the operators that are external on Operator Hub that can be installed optionally. So those aren't all available just yet, but we're working on that. But in terms of the core features, it's exactly the same code base. We're just consuming a different RPM OS tree image for our operating system.
The next question is, besides Red Hat itself, who else has large-scale footprint of OKD? Any commercial production deployments?
During one of the work group demos, I think it was Bruce Link from University in Virginia has shared that they are using OKD in production. He didn't go into details how large it is, and we cannot disclose the information about how large, how many big OKD clusters we have noticed unless folks want to speak about that privately. So the answer is yes, there are some folks are using OKD in production. No, we cannot disclose how large they are unless we would have more information from them directly with their consent.
Maybe to add to that, with OKD installations, you are not required to have any kind of tracking for us at Red Hat for your clusters. You can opt into that telemetry, so we can kind of see a little bit more about the clusters running, but you by default, you're not getting picked up if you install an OKD cluster. We have some people that do that, so we kind of see them in our telemetry data, but usually we wouldn't know who runs it. So we have some companies that are active, or people from those companies are active in the working group, and they're deploying OKD even for production workloads. Yeah, if you want to know more about that, again, please do join the working group.
Yeah, one more question. This is probably a good one for you, Dusty. What is the main difference between Core OS and other Linux operating systems?
So other Linux operating systems, I mean, probably the easiest one to compare it to, because it's so close, is Fedora, Fedora itself, or Fedora Server Edition. So with Fedora Core OS, we use a technology called RPM OS tree. I mentioned it earlier in the presentation, which is kind of like Git for your operating system. So when we build Fedora Core OS, we take the RPM packages from Fedora and we put them into this OS tree repository, kind of like a Git repository. And then we take that information from that Git repository and we create images out of it, right? So I'd say that is probably one of the biggest differences. The other being that we do use Ignition in order to provision. So with Fedora Cloud, we use Cloud Init to provision the system, like many other cloud distributions that exist. But with Fedora Core OS, we use Ignition. I mentioned that earlier. So I would say those are the two biggest pieces. Obviously being container focused and trying to separate concerns. So with Fedora Core OS, we're trying to really focus on the OS and deliver a rock solid OS, and hopefully we don't mess that up. And you take Fedora Core OS and you build on top of it by using containers, right? So your application's running containers. So that when comparing it to a traditional OS, I would say that's how I would describe the differences.
All right, and that is the last question we've got in our queue.
Awesome. Thanks again for a great presentation, everyone. And thanks again to all who attended today. A reminder that the recording and the slides will be posted later today to the CNCF webinars page. We hope to see you at a future CNCF webinar. Stay safe and have a great day, everyone.